Hi, welcome to my video. Now in this video, we're gonna do a continuation on organic chemistry. So now in this session, we are going to learn more of the geometry of our organic molecules. But just bear in mind that when we learn about the geometry of molecules, we are not only learning about the geometry of organic molecules, but also we are learning about the geometry of any other molecule that could be inorganic or so forth. Now, the theory that's going to help us to learn the geometry of molecules, it is called the Vsepr theory, which is simply says it is a valence shell electron pair repulsion, okay? So remember, when we get to organic molecules, it's very important for us to know the shapes because at some point, we're going to learn on how to determine the polarity of our organic compounds. So the shapes, learning the geometry of these molecules, it's very important, okay? So now, this is what is happening. We're going to learn, like here, for an example, we have an example, right? We're going to start by learning based on the two attachments of our molecules. Now, this molecule, it's simply carbon dioxide, right? This is a carbon dioxide. Now, let's learn more about it in terms of its geometry. Now, what you see here, it's a Lewis structure of carbon dioxide, whereby we have two attachments, but two attachments to what? Two attachments to our middle atom in this case, which is carbon. Carbon is attached to two oxygen atoms, and therefore this type of a shape, we're gonna call it a linear shape. Since, well, we have 180 degrees bond angles between the what? Between the atoms and the middle atom. So this angle over here is 180 degrees, which is a linear shape, okay? So that's easy as ABC. And therefore, we have the three attachments, whereby our middle atom, it is attached to three atoms. Now, this middle atom, which is attached to three atoms, what is the shape of this? The shape of this, it is called the trigonal planar, okay? Whereby the bond angles between these two atoms is 120 degrees. Now, what is the name of this molecule? It is an alkyl group, okay? Because you can see that carbon supposed to bond 4 times, but it only bonded 3 times. So it is what we call an alkyl group, which is CH3, and then we're going to have hyphen over there. It shows that this is a substituent or an alkyl group. So this alkyl group, what is the shape of this or geometry of this alkyl group? It is called the trigonal planar, okay? Whereby the bond angles between the atoms it's going to be 120 degrees. This angle over here is 120. Let me show you. This angle over here is 120. This angle over here is 120. As much as well as this angle over here is going to be 120. And this is what I want you to understand. This molecule, guys, hence why blood, it is flat, okay? It is flat on a surface. I'll show you a video right now of different molecules. How do we see the shapes of this geometry? It is flat. So now, since, well, it is flat, and like I said, these angles over here, it's 120 degrees. When you add all of these angles over here on the flat surface, they're gonna give you 360 degrees, okay? Which is the sum of 120s of this molecule over here, okay? So it's flat. That's very important. So when it gets to diagonal planar, just to remind yourself that these angles are 120. Tri means 3, right? So 360 divided by 3 atoms, which is hydrogen, hydrogen, and hydrogen, you get 120 degrees, so that you do not forget the angle between the atoms of this molecule, okay? And then again, we have another special case of trigonal planar, whereby the angle, it is approximately 120 degrees, not exactly 120 degrees, the angle bond, okay? It's approximately, it's getting there. So one of the reasons is because this molecule is a little bit different from this molecule. Here we can see we have a carbonyl group. These two, they look the same, okay? But they are not the same because these are not the same organic compounds. Like this has a carbonyl group and then it has oxygen. So the angles that you'll find on these molecules, the bond angles that you'll find in this molecule, it's not going to be exactly 120, but approximately 220 degrees, okay? All right. And then again, we're still under the three attachments, whereby now we have the carbon atom attached to this lone pairs, okay, attached to this lone pairs, attached to hydrogen and another hydrogen. So this carbon over here, it's going to experience the bond angle that we call it's going to experience the bond, the geometry that we call bend. Is something that is bent. Like if you bend something, say for an example, you have a stick and then you bend your stick like this is bend basically, okay? But this bend is little bit, this bend is a little bit different because now this is what is happening. Here we have CH2, okay? We have CH2. So now what you see over here, these lone pairs, okay? Because remember, carbon has 4 valence electrons. So one has bonded and one has bonded with hydrogen, and these are the remaining 2 electrons. Now these 2 remaining electrons, this is what is happening. Let me show you. Here we have carbon, and then here we have hydrogen, and then here we also have a hydrogen. And then we have the 2 pairs of electrons that are not bonded of carbon. Now these 2 electrons, they're gonna pull carbon upwards. As they pull carbon upwards, what is going to happen because of these electrons? Because the electrons, they don't like to spend much more time together. So they repel each other, hence why pair repulsion, electron pair repulsion. So now what is going to happen is these 2 electrons, they're going to strain this carbon upwards, and therefore this carbon is going to move into this position, while this hydrogen will remain at their position, and therefore this shape over here is going to be called what? It's going to be called bend. Normally the shape you will see when you get to water, this shape is less than 104, I think, comma something, but you'll see when we get to water, okay? All right, so this is bend shape, okay? So now here we have 4 attachments, no longer 3 attachments. Now this is our molecule, methane. So methane over here, the shape, it is called tetrahedral, okay? It is most definitely called tetrahedral, okay? So now this is what is happening, okay? Before I can even discuss these 4 attachments, I don't want to confuse you, but I just want to show you this video and these molecules over here, okay? Right. So now this is what you see, okay? Here we have hydrogen, we have water. Here we have carbon dioxide. We have already talked about this molecule, right? And then we have already talked about this molecule, which is trigonal planar and which is flat. You can see from on this picture, this is a flat molecule. It's flat. And then here it's a linear, which is 180 degrees angle between this. It's going to be 180 degrees. And we have learned that the angles between this molecule over here, it's going to be 120 degrees. But now let's talk about this methane over here, okay? So let me play a video so that you can see how these shapes actually looks like. So here, what you see, this molecule over here, it's a molecule of, let me pause. This is diagonal planar and it is flat on the surface, okay? And these are the atoms, okay? This is B and this is chlorine, 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 okay? All right. And therefore, we move to, let me just wait a little bit. And what you see over there, here is bent. Okay, here is bent. Bent, it is also flat. Just that these 2 electrons over here, but I'll explain this when we get to water. But remember, for oxygen, or for CH2, we had 2 electrons over here, okay? So this middle atom, and then will stretch upwards, and they will remain at the base down there, okay? It's a bend. It has bended, okay? All right. And therefore, I'm sorry about that. And therefore, let me just, And what you see over here, this is linear. We have already discussed it. It is also flat. Diagonal planar over here. And in here, it's methane, okay? This is now methane. So methane, it is a molecule that looks like this, okay? And it is called tetrahedral, okay? This is a shape or a geometry of methane, which is called tetrahedral. Now let's go back. Now we said methane, it is tetrahedral in geometry, and the bond angles of methane is going to be 109.5 degrees of our methane, okay? These angles over there, they're going to add up to 100, it's going to be 109.5 degrees. Now methane is flat, but if I have to be honest with you, it's not that flat, okay, on tetrahedral. But we have what you call the diagonal pyramidal. Ne? Diagonal pyramidal, it is almost like tetrahedral, but it's just that diagonal pyramidal will shoot upwards, just like this bend over here that I have just explained. But diagonal pyramidal, it is not flat. This is like tent, stretch tent. This is like a tent. Diagonal pyramidal, it is not flat. It's not flat because of these electrons. Now let me try to explain to you what is basically taking place here. Now here, okay, let me go back to the, this is ammonia, right? Let me go back to this video. So this is diagonal pyramidal, okay? So we have nitrogen in the middle, and then these are the hydrogen atoms. You can see that because of these lone pairs, remember, NH3, the Lewis structure will look like this, right? We're going to have nitrogen at the center. We're going to have hydrogen. We're going to have hydrogen over here. And we are also going to have hydrogen. And in there, we're going to have lone pairs, right? These lone pairs that are on middle atom, they will pull this central atom, and therefore these they will stay at their positions. They will stay behind while this nitrogen is getting pulled up, okay? And therefore this nitrogen will be pulled up, and then it will form some sort of a tent over here. This is there at the back, and then this is going to this, and this is more or less like coming towards us. So let me try to show you once more again on this video what is the shape of diagonal pyramidal, okay? Now in this video, okay, in this video here is the shape of diagonal pyramidal. You can see that this is ammonia, and in this ammonia here we have hydrogen, and at the back there we have the hydrogen, and this one is here close to us, and therefore this is nitrogen, meaning this, it was flat. It's like diagonal planar, but this diagonal planar is different because this middle atom have to rise up, okay? So this will be the shape of ammonia in this case, which is diagonal pyramidal, and then the bond angles, it's approximately 109.5 as well, okay? All right, now here we have bent, okay? Now here we have bent, okay? Now here we have bent. We have two electrons over here. These are the lone pairs. These lone pairs, they will shoot up, okay? Remember, this is flat, okay? They will shoot up. This is for attachments, these electrons, this atom, and this atom. And these electrons, they will shoot up because they don't like to spend much time together. That's why here on this shape, that's why here I'm showing that these electrons, they will pull in this direction. These electrons, because they repel each other, okay? So they can't pull each other moving in the same direction. They have to move in opposite direction to show that they repel each other. But in that process, this atom will rise up. This middle atom, in this case, which is oxygen, will rise up, and then the hydrogen will remain behind, okay? Therefore, this shape over here, it is called bend, whereby the angles, the bond angles between this is less than 104.5 degrees, okay? So these are the shapes or the geometry of our molecules. This is how we look at the geometry of molecules. If you know how to do the Lewis structure on the previous video where we discussed how to see the Lewis structure and all of that, you can now decide how to you can now be able to work out your VSEPR theory, your geometric shape using the VSEPR theory, okay? When you know the Lewis structure, most definitely. Now, I'm saying to you, this geometry, they're gonna help us to learn more about the polarity of molecules, right? Because when you talk about the polarity of molecules, we wanna know that if we have a molecule like this, does this molecule have two distinct poles or doesn't have poles at all? There are two types of molecules. When you talk about the polarity, we have a polar molecule and a non-polar molecule, okay? But first, before we can talk about the molecular poles, let us learn about the bond poles, okay? So now let us learn about the bond poles. Now, when you talk about the bond poles, we are talking about the bond inside of the molecule, right? Like, for example, we have this molecule, which is HF, hydrogen fluoride, right? This, it's a molecule, right? It's HF, hydrogen fluoride. But for now, inside of this molecule, we're going to learn about the bonds between the atoms. We call these bonds intramolecular bonds, or we can call them the interatomic bonds, okay? So we're going to learn about their polarity, these two atoms over here. So now what you see over here is, you can see that H and F, they have two distinct poles. That means the bond between these two atoms, it is a polar bond because it has two distinct poles. But if this bond didn't have positive and negative, say for example, it's positive and positive, therefore that's a non-polar bond, okay? But now how do we classify this bond to be a polar bond, to have positive and negative end? We're gonna compare these two atoms in terms of their electronegativities from the periodic table. So between hydrogen and fluorine, electronegativity for fluorine is much higher than that one of hydrogen. So that means fluorine, because it has high electronegativity, remember this type of bond is covalent bond because it's between two nonmetals and these electrons are shared. So that means fluorine, because it has greater electronegativity, will pull these shared electrons towards itself, okay? That's what we call the electronegativity, the tendency of an atom to pull the shared electrons towards itself. So that means chlorine will pull these shared electrons towards itself. And therefore now, chlorine will experience high number of electrons, high concentration of electrons, meaning chlorine will be surrounded by negative cloud of electrons. Therefore, we can say chlorine, it is partially negatively charged because the electrons are negatively charged. But now these shared electrons, because they are pulled towards fluorine, what about hydrogen? They are still shared. But hydrogen, now because of that electron has shifted towards fluorine, that means hydrogen will be left behind with proton, one proton. And therefore that will result into a hydrogen atom to have what net charge, positive net charge. And therefore would say that hydrogen, it is partially positive. Okay, so meaning this bond over here, it's between the atoms, not between the molecules. And this bond, we say it is a polar bond, okay? Meaning the dipole moment, this arrow over here, it represents what you call the dipole moment. The dipole moment, which shows the electron density or the electron concentrations, meaning these electrons will be towards fluorine in this direction to the right, okay? All right, I hope that was making sense. Now, we were talking about this molecule inside. We are inside this molecule. Now, let's have a look at another example. Let's get inside of this molecule, right? In this molecule, we're going to focus on carbon and oxygen, right? Inside of this molecule. This is also a carbonyl group. We know this molecule is organic compound. So inside of this molecule, here we have a bond again, but this bond, oxygen, has high electronegativity compared to carbon. Therefore, the shared electrons, they will be towards oxygen, meaning oxygen will have extra number of electrons towards around it. Therefore, that extra electrons, they will overpower the protons inside of the oxygen, therefore it will be negatively charged. So this will be partially negatively charged, and this carbon in this molecule will be partially positively charged, and the dipole moment will move towards oxygen. Okay, therefore this, we were discussing the polarity of the bond. Okay, this is a dipole because we have two distinct poles. Now let's talk about the molecule. Say, for example, I have this molecule and I place the same molecule between this molecule. Now we're going to talk about this molecule. Therefore, we want to know the overall charge of this molecule. Does this molecule have two opposite ends? Or, but in this case, it's simple because we can see. But now let's go here. So we're going to learn the molecular dipole moment, okay? Now, here we have an example of ammonia, right? NH3. This is nitrogen, hydrogen, hydrogen, and another hydrogen, right? So in order for us to determine the overall polarity of this molecule, that means we're going to have to use the bond polarity first. So let's talk about this nitrogen and this hydrogen. This is bond. This is a bond between the atoms inside the molecule. So we know that nitrogen has high electronegativity compared to hydrogen, therefore dipole moment will move towards N. Okay, same applies to here because this is also a hydrogen. Dipole moment will move towards N. Same applies here, will move towards N. Now this is what is happening. So ammonia, it's a molecule that looks like this. I want to show you something. We have N, and then here we have H, we have H, and then we have H, and then we have the lone pairs, right? Dipole moment. Remember, this is not flat, by the way. So we'll move over here, we'll move over there, and then we'll move over there. So meaning if I have to break these forces using physics principles, I'm going to have this component to the right, this component to the left. They're going to cancel each other. And then I'm going to have this component moving upwards. And then for this hydrogen, I'm going to have this component moving upwards. I'm going to have this hydrogen, this component moving upward, and then I add them together. So these components, they will move towards nitrogen. So that means all of these components, you see this, I have this component, this arrow, I have this component, I have that component. For this arrow, I have this component, I have that component. This component and this component. Oh, I apologize about that. This component, they're gonna cancel out, but this upward component and this upward component, they're gonna add up together, and then including this component, it's gonna have that and that, so it's gonna move upwards. So now what you see over here, the overall will move upwards. So that means this molecule, like this molecule over here, it's a polar molecule because the side of nitrogen, it will be partially negative, right? The side of nitrogen will be partially negative, and these bottom sides of hydrogen will be partially positive. And therefore, we say dipole moment will move towards nitrogen where there is a negative cloud. So that means this molecule, it will be regarded as a polar molecule. Okay? I hope that it is making sense. So now, this molecule over here, it is different from this molecule over here under this reason. So now here we have what you call the symmetrical molecules. When you talk about the symmetrical molecules, you're talking about the molecules that has equal distribution of the electrons, okay? So carbon over here, it has equal distributions of electrons on this side, equal distribution of electrons this side. This is carbon dioxide, right? And now this carbon dioxide, you have to know that this carbon dioxide doesn't have its polarity, it's a non-polar molecule, okay? It's not a polar like this one. It doesn't have two distinct poles like this one because the dipole moment moves in this. Okay, let's start with the bond. Here we have carbon, here we have oxygen. The dipole moment will move towards oxygen, which is partially negative, and carbon will be partially positive. Same applies to here. Here we're going to have partial negative, and then there we're going to have partial positive. Now let's talk about the dipole moment. These are the forces. We add them together. So this is going to the left, and this is going to the right. It's oxygen and carbon, oxygen and carbon. That means the magnitude of this is the same. But because they move in opposite directions, they cancel to give 0. So that means the net dipole moment, the net dipole moment of this molecule is 0. So that means this is a non-polar molecule. It doesn't have two distinct poles. Here, the net, this and this, and all of those components, when you add them together, they move upwards. So the net is upwards. That means here, this molecule, it is a polar molecule because it's going to have two distinct poles. Remember where arrow points, arrow head, it's partially negative. Here, it's partially positive. That means it's a polar molecule, and this is a non-polar molecule. Okay. All right. And if another example here is borane. Here's borane again, does also have a non-polar. It is also called a non-polar molecule since, well, its dipole moment is 0. Okay. That's how we describe this.